Hello everyone, welcome to this presentation that will demonstrate how we utilize resources in Advisor. Advisor is the component responsible for resolving application dependencies, and that's the component that is run in the cluster to resolve high quality dependencies considering various criteria and the quality of dependencies. So in this talk, we will take a look at a high-level overview of Advisor and how it is handled in OpenShift or in the cloud. Then we will take a look at CPU utilization and how CPU time is handled in Advisor. And the third, last section, will talk about memory utilization and how we optimize memory during the resolution process. So as stated, the very first section will be an introduction or a high-level overview of what we do in the cluster. So in the cluster, we run the resolver, and resolver accepts requirements for the application and also other information such as information about the runtime environment, information about static source code analysis of the application that a user uses, also recommendation type and other inputs that can be seen in the picture. Then the resolver or the deployment of resolver spins one containerized environment per each request, and this containerized environment runs Advisor. This Advisor is actually run in an Argo workflow that handles the whole overhead of the resolution process and providing results to users. Once the Advisor or the Advise workflow finishes, it provides information about the resolution process, information about the resolved set of dependencies, together with justification why the given set of dependencies was resolved and provided to user. Here you can see a high-level overview, and now we will take a look at how Advisor, the containerized environment, utilizes CPU, and in the next section we will take a look at how Advisor utilizes memory or optimizes memory so that the reinforcement learning algorithm that is implemented in Advisor does not end with out of memory on out of memory issues. Okay, so let's take a look at CPU utilization, and that's the first part. The main goal of CPU utilization or the Advisor is to use as much CPU as available. The whole resolution process is pretty expensive when it comes to CPU, as it needs to compute results, and it actually runs the resolution process and the reinforcement learning algorithm implemented. The very first implementation, or one of the first implementations of Advisor, used multiple processes to resolve application dependencies. However, the resolution process is not easily let's say, distributed to multiple processes, and the overhead is to distribute the resolution process into multiple processes is pretty big. It was not that successful. So we stick with one process that does the actual resolution process, and then there is one process that basically monitors the resolution process and can report any failures to users in a human readable or in a ways that is better when it comes to user experience. Okay, so let's have a look at these two processes. As stated, the first process is run to prepare inputs, and it also prepares signal handling, and then it subsequently starts process 2. Process 1 waits for process 2 to complete, either successfully or with a failure. In the meantime, process 2 resolves application dependencies and provides results, and the process that monitors process 2 once it sees the process to finished resolution process, obtains results, or if the resolution process was not successful, process 1 can propagate information about failures that happened during the resolution process. Okay, so these are the two processes that run in the cluster. By the way, if you run Advisor locally, it can be set up in a way that these two processes are merged. So you have just one process that prepares everything, runs the resolution process, and then provides results. So the cluster configuration might be different from what you experience when running Advisor locally. Now let's take a look at CPU time allocation and how it is monitored by OpenShift. The one aspect to consider here is that we are basically traversing the whole dependency graph and looking for a solution. This traversal can take forever in the worst case, because the dependency graph can be very large, and we need to have a mechanism how to limit how much time we allocate for the resolution process to successfully complete and provide results. So we basically restrict how much time we give to the resolution algorithm to compute results and find suitable application dependencies. So let's take a look at how CPU time allocation is monitored by OpenShift and which parts of Advisor check how these, or make sure that the CPU time allocated is well respected. So the first link goes to Thoth application. That is the repository which keeps deployment manifests, and you can take a look at Argo workflows. More specifically, you can take a look at, or we will take a look at Advise workflow that is responsible for running Advisor and other parts to make sure the resolution process and results are properly propagated to users. The important section here is now liveness probe. Liveness probe is executed by OpenShift. There are actually two executions of this liveness probe. So first we give some time to the resolution process to compute results. After this time, that is initial delay seconds, there is executed that liveness py script, and that does not terminate the containerized environment, but rather signalizes that soon there will be done termination. After this first notification, Advisor can continue computing results, and after some time again, it is notified that the resolution process should really stop gracefully, and if that's not the case, after 3 thresholds, it's forced to stop. So this is configuration on OpenShift side. As you might see, the liveness script is responsible for making sure that multiple executions are handled properly. So let's take a look at liveness py script. This liveness py script lives in the Advisor repository, and it's pretty straightforward, let's say. So once it is executed, it checks if there is a specific file that is maintained by this script. On the first execution, it will not exist, so the signal that is sent to the resolution process, to the process that is responsible for resolving application dependencies, is seek interrupt. Otherwise, if it does not exist, the signal that is sent is SIG-user1 and the file is created. So that's basically it. So there is distinction on these signals that are sent. If there is the very first execution of Livnet spy script, there is sent SIG-user1 signal. If there's a second execution of this script, there is executed SIG-interrupt signal to gracefully notify the resolution process to stop. Okay, so now let's take a look at resolver's handling of SIG-interrupt. SIG-interrupt, when it is received, it basically says that resolver should stop resolving, and that's it. So SIG-interrupt really says the resolution process should finish gracefully so that the resolver can obtain results, can aggregate all the results and prepare them for users, meaning serialize and these type of things. So this is handler responsible for stopping the resolution process. And then we have also that SIG-user1 signal handler that lives in predictors. And if the reinforcement learning algorithm, if a reinforcement learning algorithm is used, meaning if temporal difference is used to resolve application dependencies, here we can see SIG-user1 handler, which sets temperature to 0. That means that there's end of exploration phase, end of exploring the dependency graph, and exploration of how to resolve application dependencies, and the reinforcement learning algorithm starts to exploit the most suitable candidates for the resolution process for results. If you are more interested in these, check our articles about customizing resolution process with reinforcement learning, where this is discussed. We will take a look at it here as well. So SIG-user1 controls the resolution process in reinforcement learning algorithm. It controls exploration and exploitation phase. Very briefly, the reinforcement learning algorithm first tries to explore possibilities in the search space, meaning in the dependency graph, to resolve application dependencies. And once the resolution aggregates information about how to navigate in the search space and what dependencies are good for the resolution and which are bad, and then the algorithm can switch to exploitation phase, in which case it will start obtaining high quality results. This is modeled using temperature function that is adopted from simulated annealing or adaptive simulated annealing. So the temperature starts at some high number that decreases over time, and once the temperature hits 0, that's what we saw in SIG-user1 handler, the algorithm completely switches to exploitation phase and starts resolving application dependencies, like high quality application dependencies. Follow documentation and the articles published. If we take a look at how this is done in the resolution phase and the signal handling, first there is started exploration phase that's started in the process 2 that we discussed earlier. If CPU time allocation limit is approaching, that's the limit that is configured in the OpenShift manifest files. First, then there is sent SIG-user1 signal. This signal is sent by Livnet spy script. The algorithm completely switches to exploitation phase. Then we have some time, in which case we let the process perform exploitation, aggregate results, and also serialize these results. It will save these perform exploitation phase, resolve high quality dependencies. Once exploitation is done, after some time, that is again configured in OpenShift manifest, there is sent a SIGINT signal by Livness pipe, because Livness pipe already created the file that we saw earlier in the step 2. Advisor collects results, serializes them, and provides them to users by placing them on Ceph. Okay, so this was CPU time allocation. So as you can see, we utilized OpenShift Livness probe to manage CPU time that was allocated and is handled by OpenShift. And also there's that play with advisor. Okay, so now let's take a look at memory utilization and how we make sure that the exploration but also exploitation phase do not hit memory limits, memory that was allocated for advisor to compute results. If we take a look at manifest files used to run advisor, again, we see that there's allocated some memory. In this case, it's 6 gigabytes. By the way, you can see that CPU allocation is close to 1. As you know, there are 2 processes, so allocating more CPU would not help. There would be still utilized something like 1 processor at a time for 2 processes, because the monitoring process is very cheap. Okay, so here you see memory that is allocated, and the reinforcement learning algorithm can really go it can be really expensive when it comes to memory consumption. So we need to have a way how to constrain how much memory can be used, and how to avoid out of memory issues. To do that, let's first check how the resolution algorithm looks like, and how internal data structures used during the resolution process look like, and how we can optimize their memory consumption. So here we have a state that is maintained by a resolver. State basically states how the resolution process is proceeding, which dependencies were resolved, what was the score of this resolution, and how these resolution process explored resolution possibilities. Okay, so this is one state that is kept in advisor. This is another state, in which case the reinforcement learning algorithm decided to use another resolution path to resolve application dependencies. And we can have again another state, another path in the dependency graph, how to resolve application dependencies, and so on. So we can have multiple states. These states are kept in an internal data structure. This internal data structure is called beam. It's a beam of states, and the beam keeps naturally states, like partially resolved states that are handled by resolver. So you see basically 2 core data structures used during the resolution process. The beam mentioned is implemented in C, C++ as an extension. The first implementation in Python was slow, and there were possibilities how to optimize it as well. So the implementation is done in C, C++. You can find it in the text repository in Thoth Station organization, where it implements desired logic, which is, let's say, very specific to Thoth's resolution process. This data structure is optimized for keeping top-rated states. in which case heap queue is utilized, and this heap queue tightly cooperates with a hash map, which is used to optimize removals of items or removals of states that are kept in this heap queue. So let's take a look at it. So here you can see heap queue that in this picture keeps values, but in case of advisor, these values are directly mapped to objects, meaning objects that represent states, or pointers to objects that represent states. So here you see a heap queue. It's a min heap queue, so the top item in the min heap queue will have the lowest score in the resolution process. This is, by the way, inverted in the implementation. So this top rated will have the highest score. That's an implementation detail. So we have this min heap queue that maintains states, and now we have also a hash map that is maintained by Beam's logic, and this hash map basically maps values, meaning our states in the resolution process, to pointers where the given state is represented in the heap queue. So let's say we want to check when state v3 is present, so we access hash map. We say here is a pointer to v3 where that pointer sits in the heap queue, and the hash will respond it is kept in this part of the min heap queue. If you think about this, you see that the data structure and also the overhead here is optimized to keep top rated state. So there is always access to the top rated item, or the top rated state, and we can easily remove items from the min heap queue using shift operation that we will, I think, discuss briefly. Okay, so we maintain this min heap queue. We can easily remove items from this min heap queue, and advisor also provides implementation of memory optimizer that basically what it does, if we are approaching the current configured limit for memory, randomly remove states from the min heap queue. Keep in mind that the resolver is a stochastic resolver, so even the resolution process explores dependence resolution possibilities randomly. So the resolution process is really stochastic, and it should be okay to randomly remove states if we are approaching the limit. Okay, so let's say this is our min heap queue. These states are kept in the min heap queue, and the memory limit is approaching. So what we do, we randomly select one state and we removed it from the min heap queue. We can again remove another state, but to maintain the min heap queue, naturally we need to perform shift operation that is specific to min heap queue. Okay, so this is memory optimization. If we take a look at manifest files, we should see configuration how to optimize for memory. So we can say that this is the limit for keeping let's say memory limit in and let the memory optimizer handle this limit. And we also have other configuration options like how many iterations the memory optimizer should check if how often the memory optimizer should check if the memory limit is approaching. This is documented in advisor's documentation, so feel free to check it. Okay, so I hope the presentation was clear, and you can find more information in the documentation. So thank you for checking this talk, and see you next time.